Welcome students to today's lecture. My name is Ch20 and I am a faculty in the Department of Chemistry at Indian Institute of Technology, IIT Delhi. So, the topic we are going to discuss in today's lecture and in the forthcoming lectures is chemical kinetics as is written on this piece of paper. Now, before we go on to the details of chemical kinetics, let us try to understand the importance of chemical kinetics. So, when we say chemical kinetics, both of these words have very significant implications. So, for example, when we are talking about chemical kinetics, that means we are talking about processes related to chemistry or chemical processes. For example, one kind of change might be a reaction of A plus B, say going to C, where A and B are the products and are the reactants and C is the product. Also, now this is a case where there are two reactants which are combining to give a product, right. Now, there can be another case where I have just a transformation, for example, a state A, right, see in one phase 1 to the same A, but in phase 2. So, in the second case what has happened is I had a phase transformation. For example, say I am going from ice to liquid water, or I am going from liquid water to water vapor. That is what the second one is talking about. Now, so like this there are many examples in chemistry, right. So, if you consider these two, what they are representing is they are representing change or changes happening in whatever you are dealing with or whatever is in front of you or whatever you are working on. Then what about kinetics? Kinetics is going to tell you how fast or how quickly this change happens, right. So, if you write this, then what kinetics refers to is how fast or how quickly the particular process is going on. Then essentially what we are saying is, we are saying what is the rate of that process. Now, if you think about this, why do we need chemical kinetics? See, almost all of you have been taught or you yourself have studied about thermodynamics, the importance of thermodynamics in chemistry. Now, if you talk about thermodynamics in chemistry, what does thermodynamics tell you? Is there any need for us to go for chemical kinetics? Can we not get it from thermodynamics itself? So, let us talk about thermodynamics a little bit, so that we understand the necessity of this topic or the significance of this topic to chemistry. So, in thermodynamics, when we are talking about thermodynamics, remember, if we write and think about thermodynamics, then this is what we are focusing on. It is about the initial state, right, of your reaction or whatever, and we refer to it as I. Then you have the final state, which we refer to as F. So, thermodynamics mainly deals about these two states only, the initial state when you start a reaction and the final state. What is the final state? The final state is when you have reached a chemical equilibrium. when you have reached a chemical equilibrium, and that is why it is also referred to as chemical thermodynamics. But see, what is happening is, yes, you are talking about the initial state, you are talking about the final state, good, but what is happening in between you are not being able to focus too much on. For example, think about a certain process, say ice going to water, liquid, right. Now what will thermodynamics tell you? Thermodynamics tell you that if I have to make this transformation from ice to water, right, I would need to supply heat so that this transformation can be brought about, which tells me that the process, thereby this process is endothermic. Similarly, if I go from liquid water to water vapor, right, which is the gaseous state, again what you are doing is you are transforming the molecules, the same water molecules, from the liquid state to a gaseous state. Again you are supplying energy. So, this process is also endothermic, and thermodynamics tells you that you have to supply heat so that this process or this transformation is being brought about. Along with this, so this is only a part of it, along with this there are some other very common thermodynamic parameters that you obtain or get from these sort of reactions. So, common things you ask for is, or parameters you ask for, like the free energy change of the reaction or process, right. So, this free energy change is often referred to as delta G, and we know, so I am not going to write that, you know that which delta G is negative, that means the process is spontaneous. If the delta G is positive, the process is a non-spontaneous process. Also, you can talk about entropy changes, which is given by delta S. So far so good, right. You have the initial state, you have the final state, and because you are talking about delta G, delta S or delta H, right, whether it is delta H is endothermic, so that means you are supplying heat, or exothermic, that means heat is getting released, so delta H is negative, right. So, for an example, if you take about, if you talk about dilution of concentrated sulfuric acid, okay, let us talk about this very briefly. So, you have very concentrated sulfuric acid. What you do is you take some sulfuric acid from the chemical reagent bottle and you dilute. So, I will give you some measures of the heat that is released. This is a highly exothermic process. So, for example, suppose you are having, say this is H2SO4 in milliliters, concentrated sulfuric acid, remember you have taken directly from the reagent bottle, concentrated reagent bottle. Then you have H2O in milliliters, okay, you are mixing these. So, how you are mixing? So, suppose the volume of H2O is 100 ml and the volume of H2SO4 you are adding to this 100 ml of water is 10 ml. So, then the delta H, that means the enthalpy change of this reaction, the enthalpy change of this reaction in kilojoules is minus 11 kilojoules, right, and then the corresponding change in temperature is 25 degree Celsius. What does this mean? What it means is, when you are taking 100 ml of water, say in a beaker or in a suitable container, you are adding 10 ml of concentrated sulfuric acid, then this amount of heat is released, and the temperature increases 25. So, that is why the container feels so warm. So, this is an exothermic process, exothermic being referred to or being signified by the presence of this negative sign. Okay. Now, let us increase the volume of sulfuric acid so added. Say if you go to 30 ml of sulfuric acid, again added to the same amount of water, then the heat released is about minus 30 kilojoules and the temperature change is about 70 degrees Celsius. So, you can immediately understand, while in one case say for example, the phase transformation of ice to water, liquid water, and liquid water to water vapor, you had to supply heat so that they can make the next transformation or go to the next phase. In this case, when you are diluting sulfuric acid, concentrating sulfuric acid with water, you are having a huge amount of heat coming out or getting released, and that is why the container also feels very hot or warm depending upon the amount of temperature change you are having. Hence, this process of dilution is referred to as an exothermic process. Okay. So, then this again comes under the realm of thermodynamics, because thermodynamics is telling you that okay, this is the energy that is coming out because of the dilution, or this is the energy you have to supply so as to bring about the phase change for the previous endothermic processes. But you have to realize one thing. Now, if you ask the question, how long does it take for the phase change to happen? How long does it take for the reaction to happen, for any reaction to happen? Thermodynamics does not give you an answer for that. So, then we can write from thermodynamics we do not have any information about time. Okay. So, if I can write it again, I can say that thermodynamics gives me no time information, about time. So, the only way I can get information about the time, that is the rate at which this transformation or any transformation is taking place, is to resort to or take help of chemical kinetics. That is why this topic in itself is having such a significant place in the heart of chemistry, or as a topic it is so very important to chemistry. Okay, now, when you talk about kinetics, as we just said, we are mainly interested in the time taken, right? How slow, how fast, it is one. Also, the question is, remember when we are talking about thermodynamics, we said that calculations involved, when they include this delta H or delta G or delta S, we say that this is the difference between the final state and the initial state. So, these are the only two states we are concerned about in thermodynamics all the time. However, in case of kinetics, you start asking this question: if I have a process, so that means if I have A going to B, and if this is a process, then I start asking how does this process happen. So, when you ask this question, which everybody should, right? So, the biggest question is how, what takes place for this change to happen, then it is not only the time you are referring to, well, time is definitely an aspect, but what you are also referring to is the mechanism at the molecular level, that is mechanism at the molecular level. You need to know, if I have to go from A to B, then what is taking place at the level of the molecules in that reaction system or in that container, so that this transformation, or following which this transformation is happening, that is A is going to B. So, this also is addressed by chemical kinetics. This you can immediately understand, right, the significance. Hopefully, it is becoming a little more relevant in terms of discussion of chemical kinetics in chemistry, which is not only the rate, yes, how fast, how slow, but also when this transformation is taking place or when this process is taking place, what steps might come in, or what is the mechanism through which that particular process is happening. All these can be addressed through kinetics. Now, once you think about this, you start asking other questions, right. So, suppose you are thinking about the rate of the reaction of any particular reaction. Say I say rate of a reaction, then immediately the question that comes to your mind, can I control the rate of the reaction? If I can, what are the factors? So, that means the first question that comes to your mind is, can I have a control on the rate of the reaction? You say, I say yes. Then your next question is, great, if so, please tell me how I can control. That means, what are the factors? What are the factors? This word is factors that will control the reaction rate. Now, as we will go through our lectures, we are going to spend time on this and discuss the different factors, but I am sure most of you already know or can already realize that some of the factors are very commonly used factors that can control the rate. So, one would be concentration, then another one would be temperature. So, generally with increase in temperature the reaction rate increases, and then there is something which is a very unique, which is having a very unique place in chemistry. It is a catalyst. A catalyst is something which increases the rate of the reaction. Okay. So, that means if you have to control the rate of a reaction, so suppose you see that the reaction went too fast, you are doing an experiment in a certain laboratory. So, you are doing a practical experiment, say in one of your practical classes, and then you are following this transformation, say from A to B, and you suddenly found out, oh, this reaction just went too fast for me to capture what was happening or to capture the rate, because it was just too fast. So, how can I now decrease the rate? A, I can play with the concentration. 2, I can play with the temperature, and catalyst also has its own unique place, which we will discover later as we go through this course more and more. Okay. Now, kinetics is mainly referred to as a branch of physical chemistry. Okay. But this is generally what kinetics is thought as being a branch of physical chemistry. But you know what, if you really think about kinetics, it is actually a unifying topic. So, kinetics, I can say it is a unifying topic covering many branches. So, it has relevance in biochemistry, it is applicable in biology, right. Now, talk about mechanisms in organic and inorganic chemistry. The moment you talk about mechanisms, that is the very moment you also start talking about kinetics. Again, how fast, how slow do these things happen? Can I speed the reaction up by adding a catalyst? Can I speed the reaction up by changing the concentration of this? So, what it means is that kinetics, the importance of kinetics is not only in the branch of physical chemistry as it is supposed to be, but it really is spread over all branches, and that is why the relevance of kinetics or the importance of kinetics. And hence, I think this is a very good starting point based on which we can build on this topic or this concept of chemical kinetics. But you know, before I discuss about the rate equations and other aspects or features of chemical kinetics, I would like to discuss some examples with you in a daily life where chemical reactions and that too kinetics become quite important. So, as an example, first I will discuss about chemistry in cars. Now, you must have seen cars plying on the roads, right. Nowadays there are many cars on the roads and many different cars. There are many different car companies like Honda, Hyundai, you know, many different car companies, Maruti. Now, what happens is the way the cars run. So, at different places in cities or on the highways, you would see that there are petrol pumps where the car tank needs to be filled with petrol. Now, this petrol which the car runs on, this petrol or gasoline named as, is a mixture of hydrocarbons. Okay. It is a mixture of hydrocarbons. You can say this CXHY, right. So, the hydrocarbon I am referring to is the generic symbolism where I have X atoms of carbon and Y atoms of hydrogen, right. So, if it is methane, so suppose if it is methane CH4, then X is equal to 1, Y is equal to 4. If it is ethane C2H6, then I have X equal to 2, Y equal to 6 and so on. Now, what happens is when you turn a car on, this petrol which you had filled the tank with from the petrol pump is burnt. So, this petrol during the running of the car, the petrol is burnt, right. Now, when the petrol is burnt, so that means the hydrocarbons are getting burnt. If it is an ideal, condition, then this is typically what you would get. So, that means CXHY would combine with say the oxygen of air to give you CO2 and H2O. So, this is what you expect under ideal conditions. If the fuel I am taking, which is composed of these mixtures of hydrocarbons, are being burnt, or the fuel is being burnt, then their burning, full burning and ideal burning, why I am talking about ideal you will soon realize. So, the ideal burning should lead to the formation of carbon dioxide and water, which are not very harmful. However, what happens is, now this is an ideal case, right? Now, suppose there is incomplete fuel burning. So, that means the all fuel is not getting burnt. If all fuel is not getting burnt, then what can happen is I can have some unburnt hydrocarbon still out there. Not only that, when you burn this, what happens is you give rise to a high temperature, that means the temperature rises. When the temperature rises, and also because of incomplete burning, you can have other reactions happening. For example, this incomplete burning of CxHy can give rise to not carbon dioxide, but carbon monoxide as one of the gases is coming out. Then you also have, so this is where are you getting the oxygen from? You are getting the oxygen from air. The air is also having lots of nitrogen. So, what can also happen is that nitrogen can combine during burning to give rise to nitric oxides, NOx. So, this NOx is typically composed of NO and NO2. So, this one is nitrogen dioxide and this one is nitric oxide. So, see what has happened. The ideal condition was this. The ideal condition was that you have fuel, it combines with the oxygen of the air and it gives rise to carbon dioxide and water. This is the ideal condition, good. But then under non-ideal cases, this is typically what happens. Like when you read about ideal gas, non-ideal gas, see ideal gas is an ideal condition. Mostly all gases are non-ideal in nature. Similarly here, incomplete fuel burning gives rise to some gases which we do not want, which are poisonous for us. I will come to that very soon. But what are those gases? One is unburnt hydrocarbon, then you also have this unburnt hydrocarbon reacting with oxygen going to CO, which is again incomplete combustion, that means it does not go to CO2. You have nitrogen from the air, now which can combine at this high temperature to give rise to oxides of nitrogen represented as NOx, and under this NOx umbrella we have NO, which is the nitric oxide, and NO2, which is nitrogen dioxide. So, then in one shot I can write that if I have air plus petrol, that is what you are burning, will give rise to CO2 plus H2O, these are the ideal ones, plus CO plus NOx, these are the ones which we do not want, plus unburnt hydrocarbons. The main problem arises from these three, and that is why these three are often clubbed as pollutants or this should read as environmental pollutants. That means they pollute the environment. So, see, you are talking about fuel burning, right? You are talking about an ideal combustion, where I should be getting ideally carbon dioxide and water. I do not have much to worry about, but then because the combustion is not ideal, because of the conditions, there will be some hydrocarbons which would not be burnt. There would be carbon which would be incompletely oxidized, that means it would not go to carbon dioxide, it would rather go to carbon monoxide, this carbon coming from the hydrocarbon. And then you have so much of nitrogen in air, so this nitrogen can combine at this high temperature with oxygen to give rise to different oxides, NOx, under which we have NO and NO2. So, why are these referred to as pollutants? Now, before I write something else down, let me show you something as a picture. And if you look at this picture, and if you look at the white pointer, what you see is at the top of this picture, it is written photochemical smog. I will come to that word later, or those two words later, but remember this smog, which means that you have heavy pollutants in the air. Now, look at the picture below. What you see is, not only do you see so many cars running, but if you look at the atmosphere, it is very, very hazy. No way can you say that it is clean air that you are breathing. It is very hazy. It is hazy. Why? One of the main reasons why we have pollutants is the emission coming out from cars. So, then I can write emission from cars are a huge source of environmental pollution. It is a huge source. Okay. Now, what do cars do to stop this? So, let us look at a picture of a car. So, if you look at this car, and again if you follow my arrow, so you can see it is written as, so this is the skeleton of a car and you are seeing some components inside. I will tell you which are the main components right now we will be discussing about or relevant for our discussion. If you look at this one, this is called the exhaust manifold. Exhaust manifold means nothing, that when the engine is driving, your hydrocarbon is burning, that means your fuel is burning, then whatever gases you produce, they come out through these exhaust pipes. Okay. So, this is what is exhaust pipe A, all these gases come out through the exhaust pipes. Now, if you would not do anything to these gases, then what would happen is these exhaust gases would go straight out into the air and pollute your environment. But that is a big no-no, right, because pollution is very harmful for us, and in big cities it is directly related, that is big cities, the more the number of cars you have, the more number of automobiles you have, the greater is the pollution. So, then each and every car has to do something about it, and this is compulsory. So, what do cars do? So, each and every car is equipped with something referred to as a catalytic converter. If you see my pointer or arrow, I am moving this pointer over this word catalytic, then converter. Do not worry about the 3A, but what the catalytic converter is supposed to do is, it is supposed to take these gases, the harmful ones, and convert them to non-harmful ones, so that when finally the gases come out through this pipe, you can see out here exhaust pipe tip, then these pollutants like NOx, CO and the unburnt hydrocarbons are not there. So, this is one of the most important features, environmentally, that a car has to have, such that pollution of the environment is kept to the minimum. Okay. Now, what you see in this picture, it's a zoomed into figure of this catalytic converter. So, typically if you would be having access to a car, or if you see your neighbors have cars, your friends have cars, and if you look at the bottom of the car, you will see an object like this, very much so, like this, not too much difference in design, but the catalytic converters of most of the cars would be having this structure. Now, let us decide, or let us look at what the catalytic converter does. See, it is by the name. What does it mean? By the name, if I say the name catalytic converter, then by the name it suggests that I am converting something What am I converting here? I am converting the gases under NOx, then I am converting carbon monoxide, and I am converting unburnt fuel. How am I doing it? Because it is called a catalytic converter, so I say it is doing with the help of catalyst. Now, if you go back to one of our discussions before, when we were slowly moving into this concept of chemical kinetics, and we said that as opposed to thermodynamics, chemical kinetics tells you about the rate of the reaction and also about some idea of what goes on during the reaction. Then a question that comes to your mind automatically is, can I control the rate? And we discussed that it can be concentration, say 1, it can be temperature, second, and it can also be a catalyst which ends up changing the rates of reactions. So, that means this catalytic converter would be having some catalysts, either one catalyst or a combination of catalysts, which we will just see, which will help converting these harmful pollutants to something which would not harm us or pollute the environment. And with the idea and with the fact that the number of cars on roads, the number of automobiles, not only cars, trucks, motorcycles, everything on bikes on road are increasing day by day, it just makes sense that this level of pollution coming out or being contributed by these automobiles would increase if measures are not taken to control that level of pollutants being emitted through the exhaust pipe of the cars. Okay. So, here as we were talking, remember we looked at this catalytic converter, right. Now, what I am going to show you is the inside of a catalytic converter. Now, there is a reason we are going to this, because do understand that this is, we are talking about a chemistry in something as modern a technology as cars, with the technology improving day by day. So, now if you look at the inside of this catalytic converter, what do we see? So, the construction is very simple. On the two sides you have two ports. What are these ports? If you see this red arrow, you follow my white arrow. If you see this big red arrow, then this is the inlet port. So, the inlet pipe, what does it do? It comes from the exhaust manifold where the gases are produced after burning on fuel. So, then you can see you have those unburnt CXHY, then carbon monoxide, then oxides of nitrogen, which would enter the catalytic converter through this port. Okay. Now, the inside of the catalytic converter, you can see there are two slabs. Now, without going into the very details, also realize one thing, that these slabs are built with certain high temperature materials which can resist the temperature at which this fuel is being burnt, so that those do not get bad or not affected. But not only that, in these slabs you have catalysts embedded. So, for example, the first slab you can see out here, this slab has rhodium as a catalyst. What does rhodium do? As it is said out here, rhodium as a catalyst, it reduces the oxides of nitrogen. What is it reduced to? So, NOx gets transformed to nitrogen and oxygen. So, what does rhodium do? That means rhodium is reducing NOx as the oxide as nitrogen to nitrogen and oxygen gases. So, that is why rhodium is the catalyst. Now, also if you look at this small circle which is a part of this catalyst. So, what happens is the way this catalyst is made, or the way this this structure is made where the rhodium catalyst is there, it is porous. That means it is full of pores. Why do you need pores? You need pores so that the gas which is coming out, or the gases which are coming out from the exhaust pipe or through the exhaust pipe from the exhaust manifold, can pass through this one. During passing, what is happening is these are getting reduced, at least NOx in this case, the oxide nitrogen getting reduced to nitrogen and oxygen. Now comes the next one. Remember, you have been able to take care of the oxides of nitrogen, but what are you left with? You are still left with remember, still left with the carbon monoxide gas and then the incompletely burnt hydrocarbons. What do you do here? So, in the second slab or structure, what you have is you have two catalysts. What are these catalysts? The second one, the two catalysts are as shown, this is platinum and palladium. What do they do? They should be oxidizers. So, they oxidize carbon monoxide and the hydrocarbons. So, the next slab, which is the second one out here, have as catalysts platinum and palladium, right. They oxidize CO and CXHY. Okay. So, that means CO plus O2 gas gives me CO2 gas, right, and also remember from before CSXHY plus O2 gas. So, this is also a gas, would be giving me CO2 gas plus H2O gas. Okay. So, if I balance this, this is how it would come. So, what has this catalytic converter done for you? What this catalytic converter has done is, it has taken these harmful gases, the first being oxides of nitrogen which were reduced to nitrogen and oxygen, no pollutants. Then the ones which are coming out, carbon monoxide and the hydrocarbons, they are now being oxidized using platinum and palladium to carbon dioxide and water. By this way, and by efficient design of the catalytic converter, you can try to minimize the extent of harmful pollutants that are being given out by the car or are coming out from, you can see this blue solid arrow, this is the other side of your catalytic converter through which the gases which just got converted or some percentage which did not get converted go through. So, this is really fascinating, right. So, within that short time, and I will tell you what typically the time is, within the short time the car engine is running, the fuels are being burnt, these pollutants are being produced, these pollutants are sent to the exhaust pipe into the catalytic converter, they are passing through the catalytic converter. During that time, simultaneously what is happening is the nitric oxides, the oxides of nitrogen are getting reduced and CXHY and carbon monoxide, these are getting oxidized to less harmful or non polluting species. Okay. Now, if you go by the time that it takes, so because we are talking about kinetics, it is always good to give you some sense of time. So, the time for which it kind of stays in contact if you think about how fast does this whole process happen, or how fast, or how long does this one remain, these gases remain in contact with the catalyst, then it takes about 50 to 70 milliseconds. So, if I can write out here, so it takes about 50 to 70 milliseconds for the gas to go through the converter, right. Remember, the car is running. So, ms stands for milliseconds, and during this time this whole conversion has to take place. So, you realize that it is not only about the reaction that is happening under certain conditions, reaction or reactions, where the temperature is raised because you are burning fuel and so on, but it is also that in the catalytic converter, when the gases are passing through the two slabs where you had these catalysts, for a short time, for a very short time, the gases get the opportunity to pass over the catalysts, or in other words, the catalysts have only that much amount of time to make sure that the conversion can happen as efficiently as possible. Okay. Now, based on this, if you read newspapers, then you would come across some guidelines. What are those guidelines in terms of environmental pollution? One very common guideline for automobiles is going by that Bharat stage, say 4. What does this mean? What it means is that under this, every car, say, has to comply by the restrictions imposed under this concept or this heading, Bharat stage 4. What is it related to? It is directly related to the pollutants or the amount of these pollutants which are coming out through your exhaust. So, in the coming days, you would see that cars would have to comply by, say, Bharat stage 6. That means the amount of carbon monoxide that can come out through the exhaust, which was not oxidized to carbon dioxide, has to be even lower than what is permissible now, or the amount of oxides of nitrogen that can come out, the permissible amount would be much lower than what is being used now, which is Bharat stage 4, right. So, this was one example where chemistry in cars, along with the rates of the reaction, high temperature, high rates, right, then because of burning of fuel, then also the application of catalyst, everything is happening together, right. That is why chemical kinetics is such an important concept. So, what we will do in the next lecture is, again, before we delve into the real equations about the rate of chemical reactions and so on, we will look at another example, and if you can work on that yourself or think about that yourself, I will tell you what the example is. That example is about airbags, a safety feature in cars, and I will tell you how or what fascinating chemistry goes on in there as a direct relevance to our discussion on chemical kinetics. Thank you.